So our normal distribution. Before we even start, let me just warn you, okay? This is a term that lots of people have heard about and therefore just assume that they know, okay? There's a lot to this, and you've got to pay attention to the kind of the details and the nuances of things within this. All right, don't just assume you've got it because you've heard of a bell curve. All right? There's a lot more to the normal distribution. So let's start, first of all, by looking at what we're talking about, okay? And to set the stage here, we have a little bit of notation, but we have this random variable x, okay? In math, we have what are known as discrete variables and random variables. Discrete variables are things that just have a set value, like integer values. Or it doesn't technically have to be integers, but there's separation between the values. Here, the random variable is not discrete, it's continuous, and can be any real number. And as a result, it's kind of like geometry. You know how in geometry we have points and lines and segments and all that?
Sure.
And when you learned about a point, you found out that the point has no area and no length. It's just a location in space, right?
Yeah.
But when you put a whole bunch of points together, then you get a segment that you can measure the length of. And when you put them together in 2 dimensions, you get an area that you can find. It's kind of the similar idea to what I have written here. The probability of our variable equaling any one exact point is 0. All right? As a result, we're going to be talking about probabilities within an interval. Okay? So on a continuous distribution, it says the probability of any exact value is 0. So we find the probability of x being in an interval. All right, if I'm weighing things and the scale says 10 pounds, how do I know it's exactly 10? What if it's 9.999995 or 10.0003? Okay, because weight is a continuous variable, we can't be certain that it's exactly any specific number because our tools for measuring it aren't exact. They aren't precise enough. Okay? No matter how precise they are, it's impossible to get it perfect. Okay? So we're going to look at probabilities of a variable being within an interval. Okay? We're going to look at that in general today. We're going to look at it more specifically tomorrow using our calculators as a nice feature where we can find probabilities. Okay? Now, the next thing you don't need to write down, but I want to connect this to something that we talked about a long time ago, back in either chapter 2 or 3. And that is, every distribution has what's known as a probability density function. And for the normal distribution, it's that. Okay? It's 1 over sigma, which is, what's sigma? Lowercase sigma stands for standard deviation. So it's 1 over the standard deviation times the square root of 2 pi times e to this power. Okay? Notice in here it's negative 1/2 times x minus mu. Mu is the mean over sigma squared. Okay? Now again, you don't need to know that function, but you actually have seen that function before. Where did you see it before? Or do you remember what it was called? When we talked about modeling, we had the logistic model, the Gaussian model, okay? The Gaussian model. All right, the Gaussian model we said way back was the bell curve, okay? Here it is, and we're actually going to use it to find different values, okay? Now, check out the notation here. So you're going to see this notation quite a bit, and you need to understand what you're being given, okay? When you see this, that says that x is distributed. That's what the tilde stands for. X is distributed with a given, normally, with a given mean and variance. Okay? So you might see something like x is distributed normally, and then you'll see, you know, 72 and, let's go with 9, okay? And from that, you can tell a little bit about that information. First of all, 72 is the mean, and then 9 is the variance. So what's the standard deviation? If that's the variance, what's our standard deviation? We should know this already. This was Monday. Maybe if I show you the notation, x is distributed normally with mu as the mean and
3.
Sigma squared as the variance.
3.
So that's sigma squared, so sigma, the standard deviation, is 3. Okay? That's going to be important to keep straight. Now, one thing that you'll see done quite often, because we use the standard deviation a lot more than we use the variance, you'll see it written this way. You'll have it listed as 72, and then they'll actually write it as 3 squared and leave it like that. And that's kind of a reminder that, hey, this is the variance, but you can see what the standard deviation is. Okay? You might say, well, why don't they just write the standard deviation? Well, that's the rule. We use the variance. Okay? Now, one of the things that we need to be able to do is sketch a normal curve and also determine intervals using our mean and standard deviation. So let's look at this. Here are 3 different distributions. Okay? We have A, and it has a mean of 25 and a standard deviation of 5. So we could say that A is distributed normally. We'd write that as 25, comma, 5 squared. Okay?
Wait, aren't we supposed to put 25 instead of 5?
You can write 25, or you can leave it as 5 squared. This is a very common way of writing it, just to help you remember
That it's standard.
that it's, yeah.
Okay.
Our second one, we would say B is distributed normally with a mean of 30 and a standard deviation of 4 or 2 squared. Okay? And then lastly, C is distributed normally with a mean of 21 and a standard, a variance of 10 squared. Now, just looking at this, I want you to think, what do you think these bell curves are going to look like?
It can be like.
Compare them. Compare them. In comparison with each other.
Oh.
Okay. Okay. Steeper versus not as steep bells.
Is it going to move along the x-axis?
Okay, they will be shifted a little bit along the x-axis. For example, where do you think the mean is going to be on your bell curve?
The x-axis. Like in the middle, like in the...
In the middle, okay? The highest point on your bell curve is always going to be your mean, okay? So for example, if I'm sketching A, alright, I'm going to start right here at my mean, which is 25. And I'm going to put a point way up here. Don't worry about exactly what that value is, because to find it we'd have to go back and use that mess, and we don't need to do that for our purposes, okay? So you put your highest point there, right at the mean, okay? So yes, you're right. This one is going to be kind of between these other two. And the 30 is going to be further to the right, the 21 is going to be further to the left. Look at your standard deviations, though.
They're going to determine steepness.
What do you mean by steepness?
Like, how high the y-coordinate is versus how low it is at the same, like, distance from mean.
Okay.
The distance the low points are from the high points on the x-axis.
Okay, it determines how far away the lower points are from the higher points. So a greater standard deviation
Wider
is going to make a wider bell. Yeah. Okay, so it's going to be the difference between a bell that maybe looks like this and a bell that looks like this, right? So the standard deviation is going to create a narrower bell curve. Because, okay, the y value is kind of like, it's not, but it's kind of like what a frequency would be. It kind of tells you about how much of the data is there. So the higher the bell at that point, the more of the data is there. Okay? So here you'll notice with this skinny bell, most of our data is right here in the middle. Right? That means we have a small standard deviation. With this wide bell, our data is spread out quite a bit more.
Will the small one be like B or no?
The small one will be like B, yes. Okay? Now, when we're sketching these, anytime we had to sketch a function, we had to look for some specific points to graph, okay? And this is no different, all right? The points that we're going to look at are going to be points a certain number of standard deviations away from the mean. Okay, so for example, with A, if our mean is 25, we're going to go up 1 standard deviation, 2 standard deviations, and then 3 standard deviations. Okay? So that would take us to, if I went from 25 up 1 standard deviation, where am I? 30. And then here would be
35 and 40.
and then this is 40, okay? Now, what happens at those values? Okay, well, by the time we get over to 1 standard deviation, we've come down a little bit, okay? By the time we get to the next standard deviation, we've come down quite a bit. And by the time we're down to the 3rd standard deviation, we're really low there, okay? And you can see here, there is half of our bell curve. Yeah.
So if we're doing specific points, like, do we just guesstimate?
You guesstimate the y-coordinate, yes.
Yeah.
Okay, yeah. Now, by the time you get to the 3rd one, your guess ought to be really, really close to the x-axis. Okay? So you're showing some understanding. It's going to go down a little bit to the 1st one, more as you go to the 2nd one, and quite a bit more as you go to the 3rd one.
Oh, I got it. Sorry.
Okay. Now, we do the same thing on the bottom side. Okay? We go down 1 standard deviation, 2 standard deviations, and 3 standard deviations. Okay, so that takes us to
20,
20,
15, 10.
15, and 10. There we go. Now, this is symmetrical, so at 30 I was this high, so you should draw it symmetrically, and at 20 you should be at about the same height. Okay? Then down here up here at 2 standard deviations away, we're that high, so here I should be this high. Okay? And then at 3, you know, we should be about that far. My x-axis got a little squished. Let me try doing this. Spread this out just a little more.
Is it gonna ever touch the line or not?
No, because theoretically, in a continuous variable, it could always get bigger or it could always get smaller. Okay? As we draw this, we don't touch the line. Okay? There's the rest of our bell curve. Okay? Alright, so there's one of them. If I were to sketch sketch B, where would my highest point be?
At the first.
Third.
Yeah, at 30. Okay, so let me get rid of, that's going to be different now that we're dealing with different. There we go. Okay, so our highest point's going to be here at 30. How about our first standard deviation? How far is that going to be? 2 away. So it'll be at where and where?
32 and 28.
32 and 28, yeah. Okay.
How do you know that the mean is higher for the 30 than the 25?
Well, I know that in this case because my standard deviation is so small, it's going to actually squish it, and I'm going to have more in the middle. So it's going to push that higher.
Okay. That makes sense.
It's kind of like you have the same amount, and the more you squish it together, the taller it's going to be. The more you flatten it out, the shorter it's going to be. Okay? Again, the y-coordinate we're not really concerned with as long as it looks right. You know? So here, now we have 1 standard deviation. Okay? So we'll put it there, and equal height there. Our next standard deviation is going to put us where and where?
34.
34 and
26.
26, okay? So here's 26, here's 34, and we've gotten quite a bit lower at this point. Okay, there's 34, there's 26, okay? And then our third standard deviation will put us where and where?
24 and 36.
Good, 24 and 36. And at that point, we're very close to the x-axis, okay? And now we can see our bell curve. And you can see how it's all clustered quite a bit more in the middle. Okay? Helps if I actually hit my points. There we go. Okay? The last one, okay, this one's going to be really spread out. Alright, so we're at 21, okay, that's our highest point. It's really spread out, so I won't go too high. Then we're going up by tens, right? So here's 31, it's going to be like right here. 41 is going to be like right here, and then 51 way over here is going to be really low. So here's half of our bell curve for this one. Okay. Okay. Get a little bit of a bell shape to it. Okay. We should have made this one a little lower. There we go. Okay, and then on the other side we're at 21, so it's going to be down at 11. And then 1, and then -9, okay? So there's our peak. There's our bell curve for that one, okay? So you can see, and here's a case where if you look at those three together, all on the same x-axis, you can tell a little bit about them. Even if we didn't have these numbers, you could say, all right, well, you know, this has a much smaller standard deviation than the red one, okay? The blue one's somewhere in the middle, okay? So why do we bother getting all of this? Okay, because we can. That's one reason. That's the pure math reason. Okay? Because we can. Alright? Alright? We actually can make some observations about where our data is, and also, remember we're talking about probabilities. Okay? If I picked a random number in the data, what's the probability that it lies within a certain range? Okay? And actually, let's look at these three. What's the probability that I pick a number and it's between 25 and 30? Okay? Let's just look at that range for a moment. Okay? So here's 25. And here's 30. Okay? Now, if I look at these, you'll notice that's actually one standard deviation of my data set A, right? Okay? And actually, I know that one. That one's actually about 34%. I got about a 34% chance that if I pick a number from A, that it'll be in that range. Okay? However, with the green one, with B, notice it actually covers quite a bit more. Okay? It actually covers quite a bit more of the bell curve. Alright, now the area may look a little different. Go away. Alright, the area might look a little bit different, but look at it in relation to the rest of the bell curve. It's actually gone past 2 standard deviations, almost to the third. I'm actually going to have, if I pick a number from B, I'm actually going to have a greater probability of getting something in that range. Okay? Again, because the standard deviation is smaller. All right, so that's what we're looking at here. We're looking at probabilities. Okay, clean that back out. So, what are they for a normal distribution? And why do we care about the 1, 2, and 3 standard deviations? Well, there's a general rule here. Okay? If I go and create an interval from within 1 standard deviation of the mean, that is going to contain approximately 68% of the data. Okay? So, if I get a mean, if I get something that's normally distributed, and I know the mean is 10, and my standard deviation is 2, then if I go 1 below and 1 above, from 8 to 12, I know I have a 68% chance of landing in that interval. Okay? If I go out to 2 standard deviations, it goes up to 95%. And then 3 standard deviations is 99.5% of the data. And you can see here, okay, I kind of highlighted it for you. Here the mean was 25, the standard deviation was 5, okay? So the chances of getting within 1 standard deviation right here was 68%. As I extended out to 15 and 35, I have a 95% chance that my data will be in this range from 15 to 35. Okay? And then likewise, if I go out another standard deviation, my probability increases to 99.5%. Okay? You can see that that's the one graph that we had looked at up there. Here are the other two. Okay? Notice this one was very centrally located. The standard deviation was very small. So that 68% is just that real narrow strip right in the middle. And then there and there takes us up to 95%. And if I add on those two regions, I'm up to 99.5%. Okay? Here, because the standard deviation was so big, I need to go out to quite a larger range, from 11 to 31. I need a range of 20 in order to get my 68%. So again, look at this. Here, I have 68%. Here, I have 68%. Okay? It doesn't matter how big the picture is. It matters what your mean and standard deviation are. Okay? Yes?
Are these numbers at least, or can you like make the assumption that, for example, the green section accounts for 4.5%?
It's actually for a normally distributed variable. These percents are right on.
Okay.
Okay, it's not like, I get what you're saying with Chebyshev's theorem. At least 75% was within 1 standard deviation, or 2 standard deviations. Notice here, if it's normally distributed, Chebyshev's theorem still applies, because 2 standard deviations gives us 95%, which is at least 75%. Okay? Chebyshev's theorem applied no matter what the distribution was. Here for the normal, we can get more specific and more exact. Another thing we can look at is specific regions. Okay? Using this for specific regions. For example, going back to our first one, what's the probability that we're between 25 and 30? Because it's symmetrical and I know this whole thing would be 68%, I can figure out this little region right there is half of it. It's 34%. Okay? Or I could say too, what's the probability that it's between 15 and 20?
And that'd be like 13.5%.
Okay? Think about this. If this from here to here is 95%, and I know that from here to here is 68%, how much does that leave for these two parts?
13.5.
Okay, that leaves 27%. That has to be split up evenly here and here. So half of 27%, that would be 13.5%. Okay? So I know my probability of getting something between 15 and 20 is 13.5%. Okay? What's the probability of getting something outside of 3 standard deviations?
0.5.
0.5%. Okay? So, some neat stuff that you can do with this. And what we're going to look at tomorrow is your calculator actually will do this using the probability density function. you can find percentages for things that aren't exactly on the standard deviation barriers. Okay? For example, we could find, what's the probability of getting something between 12 and 28? Okay?
Want me to guess?
We could do that with our calculator. It actually uses calculus. Your calculators use calculus because we're actually finding area under a curve. And if you study calculus in the future, you'll find out integrals give us area under a curve. So if I found the area under this entire curve, what would it equal?
100.
What?
What?
If I found the area under this whole curve, what did you just say?
100.
100%. Because what do all the probabilities add up to?
1.
100%. Okay? So, we'll look tomorrow at how to find intervals and probabilities that way. There is a video that sums this up. You should be able to click in the PDF if you want to see an extra video to kind of sum all this up. I have some problems for you to try. These are not in your book, so make sure you get a handout before you take off, which you still have 2 minutes, so here we go.